So this is section 4.3 on the QR factorization. Okay, so what we're going to do here is we're going to find the reduced QR factorization of this matrix A, and we're going to do this using this Graham-Schmidt process that I discussed, which is a way of turning a set of linearly independent vectors into a set of linearly independent vectors that are pairwise orthogonal. Okay. And so one of the things that I'll mention is that in the book, so the A sub i's are basically the columns of a matrix A. Okay. Y sub i's are going to be orthogonal vectors that we obtain through this Graham-Schmidt process. And then those Y sub i's will be normalized or turned into unit vectors. And so the Q sub i's are going to represent orthogonal unit vectors, okay, or what we would call orthonormal vectors. Okay. So, so for this matrix here, our A1 is equal to the first column, 3, 6, 0, and our A2 is equal to our second column, that's 1, 2, 2. Okay, and so to proceed with this method, what we're going to do is we're first going to, we're going to start with A1. And so A1 we're not going to change other than we're going to make it a normal vector. So the first thing that we're going to do is we're going to compute the norm of A1, okay, which is a square root of a sum of squares. And so this is going to be square root of the 3 squared plus the 6 squared. So it's a square root of 45. And so in simplest terms, we're going to write this as 3 root 5. And so I'm going to set this R11, and that basically is going to be the 1, 1 entry of R. We're going to set that equal to 3 root 5. Okay? And then we're going to set Q1 equal to 1 over R11 A1. We're basically dividing by that norm of A1. We're dividing A1 by its norm so that we get the following. So if I divide these entries by 3 root 5, and if I rationalize, I get root 5 over 5 times the vector 1, 2, 0. Now this is a unit vector. Okay. Now I'm going to write down a formula for y2, which is going to be a vector that is orthogonal to Q1. So let's write that down. So y2, and this comes from the Graham-Schmidt process. So y2 is equal to a2, okay, and then minus, all right, we're going to do a dot product here, and I'm going to write it the way the book writes it, which is we're going to take Q1, the transpose of Q1, and dot that with A2, okay, and then times Q1. Okay, and so the first thing that we're going to do is we're going to compute this dot product here. So this is a dot product, and we're going to label this as R12. All right, so R12 is equal to A2, which is this guy, dotted with Q1. So the dot product is, so if we take the entries of Q1, and I'm going to leave this root 5 over 5 on the outside. So it looks like it's going to be a root 5 over 5 times 1 times 1 plus 2 times 2, and then plus 0. Okay, so this turns out to be root 5. Okay, so that R12 is root 5. So now I can actually write this in. A22 is 1, 2, 2, and then minus root 5 times Q1. Of course, there's going to be some simplifying here. The root 5 times root 5 over 5 is going to simplify as 1. So it's just going to be minus 1, 2, 0. And so this is going to equal the vector 0, 0, 2. Okay? And so what I want to do, so this is y2. And now y2 is orthogonal to q1, okay? And I mean, I guess we didn't define y1, but y1 is the same as q1. Okay, so y1 and y2 are orthogonal vectors. Y1, of course, is also normal, or a unit vector. But y2 is not a unit vector yet. Okay, and so we need to compute its norm. Okay, and we're going to label that as, we're going to do what we did here previously. We're going to label the norm of y2 as r22. And that's easy. I mean, the norm of y2 is, since only one of these entries is non-zero, the norm of y2 is the absolute value of its non-zero entry, which is this 2. Okay? So here it's easy to see that r22, which is the norm of y2, is equal to 2. Okay? And q2 is now just going to be y2 divided by its norm. And so that should be easy to see that, so I'll write that over here, that q2 is equal to 0, 0, 1. Okay? So I have q1, which is here, and q2, which is here. All right? And I also have r11, r12, and r22. And now I'm going to put that together to come up with our reduced QR factorization. And so I'll write that up here. So Q is equal to a matrix where I throw in Q1 and Q2 as columns of Q. So this will equal, so Q1, square root of 5 over 5, and then 2 square roots of 5 over 5, and a 0, and then 0, 0, 1. That was Q2. And then our matrix R for our QR reduced factorization is going to be, well, you can see what the entries are. I mean, I know what R11 is. I mean, I labeled this as R11 so that it goes into the 1, 1 spot here. And then R12 is this root 5. That goes here. Okay. R21 is 0. It turns out that R is a triangular matrix. Okay. And then this entry here is R22, so that's 2. Okay. So this is our reduced QR factorization, and I want you to check, and you can do this by hand or using MATLAB, that A is equal to Q times R.